Okay, now how do we handle the spherical thin-walled pressure vessel? And it's going to turn out to be a little bit easier than you might think. Right, we're going to take a slice through this sphere or ball right through the diameter and expose that one. And gee, what does that look like? Well, it looks like the end cap that we had on the cylindrical vessel. And so the development of the model is exactly the same, that the longitudinal stress is what we were developing here for that end cap and the cylindrical one. So that's pi p, the internal pressure, times d over 4t. And that's what we have for then the membrane stress and the spherical pressure, except for that's true for all directions, right? It doesn't matter whether our magician slice through this thing is vertical, whether it's at horizontal, it doesn't matter, right? As long as it goes through a diameter, it's all exactly the same. So our normal stresses is going to be the same in all directions, no matter what, right? Sigma, 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 right? And when we plot it on Mohr's circle, what we get is a dot. There are no shear stresses at all in a spherical pressure vessel, at least in theory. I say at least in theory because remember, this model only applies as long as d over t is appropriate ratio, and also if we're not near access points or any other sort of supports, anything that's a geometric kind of discontinuity. Okay. When this happens, it's called a state of hydrostatic stress, because if you look at water and how it stacks up and the pressures that are created, it's the same thing, that it will, except for it'll be in compression instead of tension, right? And so for us then, the yield stress is 36 KSI, then the longitudinal stress we worked out in the previous example is 10.2. That's where the answer 3.52 would then come from. Really simple and straightforward for the spherical pressure vessel.